Megadams. Superstars of civil engineering which contain hundreds of millions of cubic meters of water. Some produce electricity on the scale of nuclear reactors solely by harnessing the force of water. Yet building them requires gigantic effort. They're truly pharaonic sites, often pulverizing records. Like that at Serre Ponçon in the French Alps, which in 1959 achieves fame as the biggest barrage in Europe.
The mass of material amounted to 14 million cubic meters of earth and stone. That's 6 times the Pyramid of Cheops.
Yet how do you erect a wall 120 meters high? With machinery never seen before on a site. How did the workers transform a valley into a stunning artificial lake? Other barrages seem modest in comparison, yet they hide plans of extraordinary output. Such as at Romanche-Gavet, where they built the power station inside the mountain. Erecting several hundred tons of machinery in rock caverns up to the height of a 7-story building. Another superpower plant has even topped this feat, Grande Maison, where it took 10 years to dig a conduct, providing the steepest onrush of water to get the maximum impact at its point of arrival. Where the only possible site required a truly mountainous effort.
A barrage 160 meters high. That's half the height of the Eiffel Tower. We felt like ants. How could we ever achieve this?
Yet the water doesn't stop at the base of the barrage. The miners elongated the conduct into a vertiginous slope 1,000 meters long. With a pressure of 100 bars, the hydraulic power driving its turbines makes Grande Maison the most powerful hydroelectric plant in Europe. Creating a vertical conduct 3 times the size of the Eiffel Tower is an absolute first. Grande Maison, the most powerful barrage of them all. Romanche-Gavet, the technically most advanced. Serre Ponçon, one of the largest construction sites ever. Amidst towering mountains, megadams of stupendous dimensions. We have always constructed barrages. A dam placed across the course of a stream provides a reservoir and allows its water to be used by deviating it. It's been done throughout the ages to irrigate fields. At the end of the 19th century, an additional way of using water becomes available, particularly in the Alpine region. Masses of water can be led through subterranean conducts. And be used to drive turbines and thus generate electricity.
We can go from 0 to 1,800 megawatts in less than 3 minutes.
An amount of power comparable to that of a nuclear reactor. Yet it takes years, if not decades, of study and toil to get there. It calls for mastering the environment to provoke a cascade of water able to set the heavy machinery in action. Requiring equipment never seen before in France, the creation of an artificial lake. Building the highest dam in Europe, a sight out of all proportion. Serre Ponçon is a giant among giants, making the dream of civil engineers come true.
At the beginning of the 20th century, an engineer named Yves van Willem came up with the idea of a barrage across the river Durance in southern France. He identified Serre Ponçon as the ideal site because that's where the river passes through a natural bottleneck between two rock formations.
The location may be perfect, however, the technology of the time doesn't allow for a project of such size. It amounts to nothing less than to block the river by a dam, to transform the valley behind it into an immense lake, and to dig a tunnel to lead the water to the power station. The challenge is too complex, and the dimensions defy the possibilities of the day. It takes half a century before the nation's industrial capacity enables engineers to construct a barrage in the valley. Its objectives: to produce electricity and to protect the local people from the devastating impact of an uncontrollable river. Thanks to its forceful currents, a hydroelectric power plant can be fed with energy. Yet to achieve this, shafts have to be dug within the mountains through which the water can be rushed to propel the giant turbines. The site is that envisaged by Yves van Willem, the narrowest gap of the valley. Yet the future dam will have grave consequences for those living below.
Building a barrage means flooding a valley.
At Serre Ponçon, transforming the valley into a reservoir enforces a near-biblical exodus of several hundred families. The man-made deluge spells the end for two entire villages: Hubei and Savine. Both have to be evacuated. It's a major operation in itself.
They tell you, we have to raise your village. We had 1,500 inhabitants at the time, 3 factories. It was really painful. Whole families were displaced.
The villages are blown up. EDF, the state-owned electricity company, agrees to rebuild a part of Savine a few kilometers further on the banks of the projected lake. The new village will be called Savine-le-Lac. And so, before the valley will be flooded, it becomes the site of another major construction feat.
One of the outstanding features of Serre Ponçon is the road bridge, intended to link the two lake sides once the valley is flooded. It's almost 1 kilometer long.
The new bridge allows the villagers of Savine-le-Lac a day-to-day view of the progress of the dam under construction. The foundations of the colossal barrage require a dry site. It's impossible to erect a dam that size across a running stream.
So the first task was to detour the riverbed.
It's a crucial prerequisite. The miners must drive a shaft into the mountain to deviate the river away from the actual site. 600 meters upstream, a new star in the realm of megastructures makes its entry.
To pierce the rock, they brought up engines called jumbos.
The jumbos are an invention of the 1950s. A scaffold weighing 70 tons holds 15 compressed air drills. A mammoth like that had been used to dig the Mont Blanc tunnel. This one is a reduced replica, devised to drill 2 shafts, each one 4 meters in diameter and 900 meters long. Thanks to the jumbo's drills, the miners can place their explosives deep inside the rock, which is far more effective than detonating them near the rock face.
fait tout sauter. Une fois
Once you've pushed the button, you remove the rocks from the floor and start again.
On évacue tout ça et on recommence.
This stage alone takes several months, as the drills have to dig 2 parallel galleries. With a total length of 1,800 meters and a combined diameter of a little over 10 meters. However, to send water through these conducts, it takes a barrage of its own.
They had to construct a smaller reservoir upstream to divert the river.
The barrage of 14 meters in height has the sole function of deviating the Durance and the Ubaye River into the 2 conducts. The water thus rushes right through the mountain and ends up in a small lake. But that's not the end of it.
Once the river was deviated, they could work on dry soil to construct the actual barrage.
Yet before that, it's necessary to prepare the foundations. The water must not only be kept from seeping into the dam, but also from forcing its way underneath it. Sealing off soil several meters underground is a first and a major challenge.
They came up with a technique which allowed the soil to be plugged by deep drilling and by injecting a mix of concrete and clay called bentonite. This procedure was crucial for being able to construct a barrage at Serre Ponçon.
With the foundation sealed off, work on the 2 sides of the dam can begin. To raise the barrage, the planners decide on using local material. It's a matter of economy in terms of transport, but also determined by the characteristics of the rocks. They comply ideally with the required water tightness.
You need incredible amounts of soil and stone to erect a barrage like this.
Yet the dam isn't merely a gigantic heap of ground rock. Its core constitutes its strategic part, which has to withstand the immense pressure of the lake behind it. And again, the proper material isn't too far away.
The inner dam is made of clay from the Provence region.
Est fait avec de l'argile de Provence.
It's soft, flexible, and dense at the same time. All the qualities needed to hold back millions of cubic meters of water. The core rises as 50 tons of clay are delivered each day.
At the bottom, the clay is much more condensed due to the pressure from above, and so little by little it took the form of a pyramid.
A pyramid more than 100 meters high, the size of London's Westminster Abbey, with a volume of 2 million cubic meters, flanked by slopes of 6 million cubic meters each. It's the first time that such a mass of material is heaped up in France. Impossible to imagine a site like this with conventional trucks discharging the enormous rocks. Here too, lorries out of all proportion are indispensable.
They needed truly colossal means of transport, and after quite a search, came up with so-called Euclids, trucks with a payload capacity of 45 tons.
The Euclids weigh 40 tons themselves and are imported from the United States via the port of Marseille, 200 kilometers further south. The convoys take 5 days to reach the site. Dozens of strange vehicles fitted with enormous containers or gigantic shovels, some of them moving rocks of 80 tons, are active around the clock. Between 1955 and 1960, 3,000 men are working at the site. From time to time, work is interrupted to give way to experts on hydroelectrics. Their task is to install sensors. They will function for decades and deliver data from inside the dam. They monitor the tiniest movement or register infiltrating water. For lack of access, however, they can't be replaced once they're fitted. The sensors are installed at every critical point of the barrage, especially in the core. It takes 5 years to raise the dam to its full height of 124 meters and its base length of 630 meters. The result is a modern pyramid, the greatest barrage in Europe. It may be spectacular, yet what happens at its base, although less visible, is astounding too. Here, they've dug caves of several hundred square meters, housing the turbines. Water rushing down at high speed from the barrage will turn their blades, creating electricity.
A turbine with its shaft and its equipment above adds up to around 15 meters. We're talking about a weight of 300 tons.
These mechanical monsters, driven by the force of water, make Serre Ponçon the most powerful hydroelectric plant of its time in Europe, capable of supplying a city of 300,000 inhabitants. Once the 4 turbines are installed, the entire complex can be put to the test. Will the dam hold? Will the water follow its destined course and arrive with the intended speed? Will the turbines react to the onrush of millions of liters of water? At the time, it's a first, so tension is high. In 1959, the actual construction is finished. It's time to start flooding the valley. Experts, workers, and onlookers, no one wants to miss the moment. On November 16, 1959, the small dam that served to deviate the water into the tunnels is demolished. Then, the 2 conducts are closed. The water will rise behind the Great Dam. However, it will take a whole year until the reservoir is filled up. Slowly, millions of liters of water inundate the valley. It will hold the equivalent of 500,000 Olympic-sized swimming pools. The villages of Savines and Ubaye disappear under 30 meters of water, giving way to an incredible man-made reservoir, which boasts yet another record.
It's the largest artificial lake in France, holding 1.2 billion cubic meters of water.
A bit further on, the piers of the road bridge linking the new village of Savines-le-Lac with the opposite bank seem to shrink day by day.
They're 40 meters high, but once the valley is flooded, the bridge runs a mere 2 meters above the water level.
À simplement 2 mètres au-dessus du niveau de l'eau.
It takes 18 months to reach this level. The trial run to produce electricity can be initiated. In May 1961, production proper can finally begin. The shafts, which had diverted the Durance and the Ubaye River to ensure a dry site, are reopened. The water starts rushing through the 2 subterranean conducts until, after 900 meters, it's stopped by gigantic valves. Inside each one, there's an oval slab weighing 45 tons, and that's 3.5 meters wide.
It's like a lens obstructing the oncoming water. To open the valve, it's moved into a horizontal position.
However, it's impossible to move the lens against the phenomenal pressure of 100 bars. a special stratagem is called for.
The water is directed through a smaller pipe and thus passes above the valve until the pressure behind the lens is equivalent to that in front of it.
Without this detour, the mass of water would make it impossible to move the lens. Once equal pressure is achieved, the lens is tilted by a supersized lever moved by hydraulic jacks. It pivots the lens into a horizontal position. The high-speed rush of water is led through a conduct onto a wheel weighing dozens of tons. Once it hits the compartment walls, the wheel begins to turn, and with it, the camshaft. To create electricity, an exciter above allows tension of 1000 amperes to be sent into the turbine.
An average house is calibrated for 30 ampere. Now 1000, that's a bit of a difference.
The turbine rotates at 400 revolutions per minute. The rotor and the stator deliver immense magnetic power, and electricity begins to flow. It's a superb feat of engineering. In 1960, Serre Ponçon is the biggest barrage in Europe. Supplying 300,000 households, one of the greatest construction sites in history has delivered a technical triumph. The barrage of Serre Ponçon is a marvel in itself, a stunning sight, not least because of the beauty of the newly created lake. A single building is a reminder of the history of the valley. A small chapel 700 meters above sea level was spared by the rising flood. Serre Ponçon has become an emblematic site due to its history as well as to its exceptional performance even 60 years on. Yet, only a few kilometers away, there is a rival in terms of modernity. Since 2020, Romanche-Gavet exemplifies the future of hydroelectric plants. 10 years of construction and an invisible power station entirely built inside a mountain. Yet how do you create a hollow that size from the Alpine Massif? A unique rotary digger shield takes on the challenge.
It's not an ordinary drill. It's not made to pierce the rock, but to eviscerate a mountain.
To provoke a sufficient downward flush of water, you need to dig a well inside the mountain, measuring more than 3 statues of Liberty piled on top of each other. To achieve this, you need to dig down from the top of the massif and find a means to put in place heavy machinery. The size of the turbines intended for the enormous caverns is immense. They're up to 7 stories high, each weighing more than 50 tons. Assembling them calls for precision, right down to the last millimeter. Yet perfection is paramount, since the turbines will be rotating at full speed. Daily output of the plant will be on a scale never achieved before.
The special feature of Romanche-Gavet in the history of hydroelectrics is that the new plant was intended to replace several other older plants from 2020 onwards.
6 small plants along the banks of the Romanche River will be shut down. Their combined power of 50 megawatts is no longer deemed sufficient for the region. Yet the new plant shall not merely replace them. The aim is to increase the overall output by 40%.
That's the average consumption of a city of 60,000 inhabitants. It's the first time an augmentation of that size was to be achieved while replacing existing plants.
It means nothing less than achieving 97 megawatts, 2 times the power of all Google's servers combined. It's an ambitious project, Research and analyses of the terrain have been going on since the early 70s. The planned output requires exceptional hydraulic power to drive the turbines. Therefore, the engineers decide to create a shaft which will cause the water to arrive with extreme force. 9 kilometers from the future plant, a barrage will deviate the water into a long conduct. Yet first, they have to prepare the terrain.
We rerouted the river from its natural bed into the provisional canal so that we'd be able to undertake all the digging and construction of the barrage, protected from any flooding from the river.
To safeguard the workers, gigantic nets are spread on the flanks of the Baldona Massif. Thousands of square meters of them are fixed by expert mountaineers in a way that resists falling rocks of several tons.
They're the kind of nets used to protect harbors against submarines. Here they were used to secure the slopes of the mountain.
To build a barrage below cliffs of up to 1,500 meters in height is risky. Even more so, as work at this site requires several months. It's a complex undertaking.
The barrage consists of piers of concrete 13 meters high, separated by gates.
The gates will raise the level of the river. The overflowing water is thus deviated to the right, where the plant's water supply is under construction. The barrage isn't intended to hold back the water, but merely to reroute it, a method that's called to go with the flow.
When the river runs high because of melting snow or consistent rain, the output of electricity will be higher. During dry periods, we'll produce a little bit less.
A certain amount of water is led into a channel made up of walls 10 meters high. These banks of concrete will direct the flux into a conduct deep inside the mountain. Thousands of liters of water will follow a trajectory of 9 kilometers through solid rock until there's a brutal drop of 160 meters leading to the turbines, which will produce the electricity. Digging the shafts calls for all sorts of machinery.
The barrage has the sole function of diverting the water into the gallery. The other two-thirds of Romanche-Gavet are all underground.
To be able to work in the heart of the mountain and to dig a 9-kilometer shaft, the team turns to the latest technology, true monsters of tunneling.
A rotary digger shield is 4.7 meters in diameter, 200 meters long, and weighs 600 tons, and all that on rails.
2 specimens arrive at the site, still dismantled. Once the mammoths are put together, they will force their way into opposite directions. One will start from the left towards the power station, 3 kilometers away. To get there, it will take 18 months. The other one digs towards the barrage, covering a stretch of 6 kilometers. Allocated time span, more than 2 years. However, these mega drills are hindered by their length. To be able to get going in the proper direction, they have to tunnel their own access first.
These machines are 200 meters long. If you want to do a right-angled turn, the curve has to be very long. To turn a rotary digger shield, you need a bend of nearly 1 kilometer.
The digger shields rotate day and night. Time is crucial. 3 teams work in relays to advance the monster's work non-stop. Thus, a stretch of 12 meters is dug each day. It's a process of stunning efficiency. The giants block themselves by pressing grippers against the surrounding rock.
It's like two large paddles which push sideways against the rock. Once the machine is blocked, it's pressed forward by enormous hydraulic jacks. At the same time, the shield begins to rotate.
26 dents, called calves, are fixed on the shield, each weighing about 50 kilograms. 5 specialized workers take turns inside the machine to check its state and monitor the parameters relevant to its advance. Density of the rocks, hydrometric data, proper alignment of the dig.
It's actually like a little city, a little factory on the move.
The Beldone Massif is made up of gneiss. It's notoriously hard and hinders rapid progression, yet it has a particular advantage. Inside the tunnel, there's no need for voussoirs, elements of concrete which serve to consolidate the walls. The gallery sustains itself. So retaining structures can be dispensed with. But then, the engineers are confronted with a problem.
Once you start, you never know what you'll encounter.
A stretch of loose terrain with crevices and mud halts the advance. The rotary digger shield lacks lateral grip and is unable to push itself forward.
Our famous paddles, well, they pressed and pressed and pressed.
Without its holds, it's impossible to move the shield forward. The experts had dreaded just that. 200 tons of machinery are stuck. The solution? To fill up the cavities with hundreds of liters of concrete. It's intended to offer the paddles a fixed point. And it works. The mammoth starts moving again. Meanwhile, 9 kilometers from the barrage, work begins on another gigantic site. Here, they're digging the caverns.
A construction like this, inside a mountain, was exceptional in any respect. We had to resort to digging techniques which were completely different.
2 caverns are to be created inside the mountain. The main one, 74 meters long and 35 meters high. Dimensions that surpass the nave of Notre Dame in Paris. In here, EDF, the company which will exploit the barrage, plans to install the enormous turbines and alternators which will produce the electricity.
We needed sufficient space for mounting the turbines and to dismantle them for maintenance.
Access for the turbines and the alternators is provided by a gallery of 200 meters, pierced into the rock by drills and explosives. Parts weighing dozens of tons have to be assembled vertically. They'll make up a machine 26 meters high, the equivalent of an 8-story building, with the transmission shaft in its center. It takes weeks to configure all elements. Some weigh as much as a Boeing 737. Maneuvering them requires the utmost attention and supersized lifting apparatuses. In spring 2017, the traveling crane is put to the test, with a charge of 118 tons to be lifted for 1 hour. Its capacities are crucial for the assembling stage. There's the wheel, which is to be moved by the onrushing water. Then there's the 70-ton rotor. It will be driven by the wheel and rotate in the fixed part of the design called a stator. It's the interaction between rotor and stator which will create electricity.
The precision required is diabolical, especially when aligning the shaft to the alternator. It's a matter of micrometers.
1/1000th of a millimeter with monsters of several tons. Few enterprises in the world are capable of manufacturing parts with that degree of precision. Yet it's indispensable if the whole setup is to run without friction.
Wheels, shaft and stator combine to almost 100 tons that will be rotating at 500 revolutions per minute.
If it's badly adjusted, it may overheat or tear itself apart.
A delicate stage during which another complex operation takes place outside. Driving a shaft into the mountain.
It means digging down vertically for 180 meters. That's like a high-rise with 60 floors. Actually, it's more like a tower.
Its function is to avoid the so-called water hammer, an effect which occurs when a valve is closed too quickly. If the oncoming water is stopped too abruptly, it'll be forced back violently, causing the entire pipe system to tremble. And with huge amounts of water like here,
it will create a surcharge of pressure within the massif. It may even cause a rupture and a collapse of the galleries.
To avoid this, the flux of water must be provided with an outlet. When the valves of the plant are closed, the water will flow into the shaft, and the well-like column will relieve the pipe system of the pressure. An installation like this is indispensable, yet it constitutes a true challenge. Piercing a mountain massif vertically calls for a technique totally different from horizontal tunneling. It's called raise boring. It's based on a cross which will be moved upwards by a telescopic pole. The supersized selfie stick is assembled on top of the mountain, which is a major feat in itself. That's where they also have to lift the apparatus which is to drive the pole. Not that easy, as it weighs several tons.
How do you get all the parts of the raise boring up there? At that height, almost any helicopter was at the limit of its performance. However, we found a Super Puma which, after being slightly modified, was able to lift 5 tons.
It's one of the most powerful choppers in the world. It can carry 20 passengers at a speed of 280 kilometers per hour. It's mainly used for maneuvering under difficult conditions, like when supplying offshore platforms. It must lift the entire material 350 meters up from the hydroelectric plant. A platform is constructed to provide a space for working without risk. It's the size of a tennis court, requiring 210 cubic meters of concrete. "120 sections of 1.5 meters and 700 kilograms each are brought to the top of the mountain.
A claw then picks up the section and turns it from the horizontal into a vertical position.
The sections are screwed into each other and form an immense pole inside the mountain, stretching down into a cavity 160 meters below. The device which will bite into the rock is fitted to the lowest section. Then the entire system rotates slowly upwards.
Between each arm of the cross, there is a space through which the material will simply drop down.
The cross grinds its way upwards. The procedure may be slow, yet it allows for a shaft of 5.5 meters in diameter. Raise boring a shaft that matches the height of the second floor of the Eiffel Tower is a record in French engineering.
There's a limit as to the diameter and the length of a shaft. To drill that way, you need engines of phenomenal power.
At Romanche-Gavet, raised boring is used at two sites, to drill the pressure-relieving shaft, as well as to create a vertical gallery. Through it, the water will plunge abruptly after the 9 kilometers of slope from the barrage, rushing to the level of the turbines 163 meters lower down. It's an instant of extreme violence. Millions of liters of water have a tremendous impact.
The most sensitive part comes right after that. You're really in the realm of high-end engineering.
The workers have to insert steel sections of 3.3 meters in diameter. They'll secure the walls of the shaft along its length of 163 meters. A complex operation, dangerous, yet essential. The pressure and the speed of the falling water are devastating. The tube must be consolidated. The single sections are welded onto each other. Then, concrete is injected between the steel and the rock to ensure maximum solidity. It's the final stage at Romanche-Gavet. In 2019, it's time for the trial run. The barrage is lowered a bit and the water of the river is diverted into the channel. After 9 kilometers down the conduct, everything goes according to plan. The water plunges into the vertical gallery and starts the turbine by transferring its force onto the master wheel, which drives the central shaft. The 70-ton rotor begins to rotate until it runs at 400 revolutions per minute.
And the rotor, via the stator, will create electricity.
The energy released amounts to 10,000 volts, yet the transformers will even boost that output. These giants are filled with about 20 tons of oil, giving them a total weight of 63 tons. When they receive an electric current of 10,000 volts, they will multiply this more than 6-fold.
Romanche-Gavet will produce 560 gigawatt hours per year. In other words, the consumption of 230,000 inhabitants.
For 10 years, Romanche-Gavet is the biggest hydroelectric plant in France. But then, it's dwarfed by a new neighbor. Laid out for a capacity of 97 megawatts, Romanche-Gavet is topped by a colossus of 1,800 megawatts. The barrage of Grande Maison.
It's the most powerful hydroelectric plant in Europe.
Its power of 1.8 gigawatts is the equivalent of 2 nuclear reactors.
Constructing a plant of such dimensions is a vertiginous undertaking, with galleries causing the water to fall for 1,000 meters, 3 times the height of the Eiffel Tower.
Grande Maison is the jewel in the crown of construction technology.
It's an exceptional design, also because of a revolutionary operating cycle. The water which will drive the turbines is pumped back 1,000 meters up into the lake. Thanks to an ingenious system, it can be used continually to produce electricity. Grande Maison is a barrage which accumulates records. As early as the 1970s, engineers begin to look for a site that will allow the construction of a plant capable of achieving the envisaged performance. They decide on the foot of the Grand Russe Massif. 1,700 meters above sea level, rain and glaciers will provide for an abundance of water. Yet to realize a barrage up here, they have to beat the record of Serre Ponçon and erect a dam as high as Notre Dame Cathedral.
Imagine building a barrage 160 meters high in layers of 30 centimeters.
Yet first, they have to reroute the stream, which runs through the valley, in order to obtain a dry site. In 1978, work begins. A tunnel is dug inside the mountain. Here too, a monstrous rotary digger shield weighing 500 tons and 200 meters long pounds its way through the rock. It'll take 2 years to cover 7 kilometers. Then a huge shaft will be dug. At 1,000 meters, it will top the Burj Khalifa Tower in Dubai.
A drop like this amounts to 100 bars. That's 100 kilos per square inch.
The water will fall at a speed of 18 meters per second. To achieve such a radical descent, they'll have to dig 3 shafts, each 4 meters in diameter. Work at the various sites is conducted at the utmost speed. It's a race against the clock, since there's an enemy which may disrupt all plans: snow.
Work was possible for 5 or 6 months. Everything depended on the weather. Back then, in the 80s, winters were still extremely severe.
Work continues around the clock. At dusk, 5,000 kilowatt hours of electricity help flood the site with light. The equivalent of 5,000 washing machines running simultaneously.
It was as bright as daylight. We had extremely powerful illumination.
7 years after the first mechanical excavators set to work, the barrage is completed. The preliminary studies for heaping such an amount of rock are validated. The result is astounding.
Having reached 160 meters, there was a difference of just a few dozen centimeters.
Work has been accomplished at a furious pace at all levels. 140 million cubic meters of material have been amassed at 1,700 meters above sea level to erect the dam. Galleries have been driven into the mountain. And 1,000 meters below, the new power station has been installed. It's here that the monster turbines will rival the output of a nuclear reactor. Their dimensions are proportional to the power of the onrushing water. 12 turbines are placed in one huge space, each 40 meters high and driven by wheels of 18 tons. They will deliver 15,500 volts, a current the transformers will boost to 400,000 volts. Sufficient energy to supply the cities of Grenoble, Chambéry and Lyon at the same time. And it all comes from one single lake. Europe has never seen anything like it.
Grand Maison is nicknamed the EMS of the electricity net. When there's a problem somewhere, say a major power cut, Grand Maison can mobilize all its power in 3 minutes.
It's an unequal power, thanks to an unequaled new system. The engineers of Grand Maison have installed a second plant. It boasts turbo pumps, engines which allow a unique mechanism to be used.
The system is completely reversible.
The water used to drive the turbines is simply pumped back to where it came from, 1,700 meters above. 100 meters below the turbines, which generate the electricity, they have dug a second cave for 8 turbo pumps, each a dozen meters high. They're inverted turbines, which pump up the water from the small basin into the Great Lake. The planners of Grand Maison have won their bet. 4 wheels, 2.3 meters in diameter and weighing hundreds of tons, rotate at 600 revolutions per minute. This enables them to send back vertically the equivalent of a 50-meter Olympic swimming pool every 18 seconds. This technology permits the same water to be used continually and thus be independent of the level of the lake. Yet the operation is most sensitive. It's a tour de force bordering on madness to pump out a lake and send it back up more than 1 kilometer above itself. To test the turbo pumps, first of all the lake has to be filled up by water from the glaciers and the rains. It's a process that takes years.
It took from 1984 to 1987.
Finally, the lake of Grand Maison is filled with 140 cubic meters of water, covering 2 square kilometers, providing the intended amount of pressure. Able to supply 700,000 inhabitants with electricity, Grand Maison beats all European records in terms of output. Except for nuclear power, there's nothing comparable in this field. The world over, megadams are being planned, such as Inga 3, situated on the banks of the Congo River. One day, it may produce the equivalent of 20 nuclear plants and supply 40% of the demand of the African continent. In Europe, however, such super plants are barely feasible anymore. The mentality has changed, and interfering with the environment on such a scale is viewed with extreme doubt. The great barrages of Serre Ponçon, Romanche-Gavet, or Grand Maison have become benchmarks of civil engineering. They will continue to stand out as mega construction projects that defy the imagination.